Hello, my name is Hamed Okravi. Today I'm going to show you a demo about Trusted Boot, and what we are going to see in this demo is that an attacker is going to install a malicious kernel which contains a rootkit on the other machine, but with the trusted execution technology feature of Intel and Trusted Boot, we can detect this malicious attack and prevent booting into the malicious kernel which contains a rootkit. Now, what we have here is this is the machine that has Trusted Boot. Right now we are in vanilla Linux without Trusted Boot, so this is vulnerable to attacks. It is connected to the other machine using a serial link, which we can see in the back, so that the other one can capture the console messages at the boot time, and it is also connected through a LAN so that we can attack the victim. Now, what we have here right now is that a daemon is running which contains a buffer overflow vulnerability. Now, the other machine, we have a script here which can send a payload. If we look at the script, we netcat a payload into this machine, into the daemon, and what this payload does is that it exploits this buffer overflow vulnerability, and as a result it can run a shell script in the victim's machine. When we run the shell script, we can download a malicious kernel from a server, which is not here, from the internet, and install that kernel which contains a rootkit. And then the next time this machine boots up, it boots into the kernel which contains the rootkit, and then we can exploit that rootkit to gain access to this machine. What we want to do is to prevent that using Trusted Boot. So let's do it. Let's send the payload now. The kernel, the daemon is running here. I send the payload. And what it does, if you look at the messages, is that it downloaded a kernel, infected kernel, from a server, installed it on this machine. So now this machine, the kernel of this machine, contains the rootkit now. So let's boot up. I'll show how Trusted Boot can detect this attack. So what it does is that we have the kernel, the good kernel, stored on the TPM chip, Trusted Platform Module chip, on this machine. And there's a policy to check that hash value, which is called also the measurement, at the boot time. Now, when this machine at this boot time wants to check that measurement, it fails because the new kernel contains a rootkit which with a different hash, and we'll show how it fails to boot. Okay, now we choose to run Zen with Intel Trusted Execution Technology. As you can see, it outputted the messages from the boot time messages to this console from the serial link. But essentially, what it shows us is that it says the installed component do not match the verified launch policy. Basically, it means that the measurement or the hash value doesn't match what we had on the TPM. So Trusted Boot prevented this attack from taking place and prevented the malicious kernel to run. Now, what I want to do next is to go back and manually fix the kernel, put the correct version of the kernel, and then boot up and show that Intel Trusted Execution Technology will boot into the good kernel. So what I do now is to turn off this machine, turn it back on. I'll boot into a normal version of Linux, Fedora, and go and manually fix the malicious kernel. Install the good kernel. All right, so we log into the victim machine. The attack left a signature on the desktop of this machine, which basically shows that this machine was attacked. So to fix the problem, we go to the boot directory and remove this malicious kernel, and we have a good kernel here. We rename it to the kernel that we want to boot from. Alright, so now we changed the kernel back to the good kernel without any rootkit. So let's restart, and if we're successful, we should be able to boot into this kernel. The policy matches the measurement of this kernel, matches the value that's on TPM, and then it should be successful to boot into this kernel. Alright, so it is restarting. Okay, we again go to Zen with Intel Trusted Execution Technology. We boot there. Now it is successful. So now the policy matches the stored version on TPM. We are successful to boot into this kernel. So it shows that we can detect any malicious kernel at the boot time using the trusted boot feature, and this prevents rootkits, any extra modules in the kernel, and any malicious software to be installed on the system, because if those things happen, then the measurements don't match and we prevent booting. Thank you very much.